And another way that you're going to see electron configurations is orbital notation. And what orbital notation does is it takes the concept of standard notation and expands it a little bit to visualize the Pauli exclusion principle, that idea that you can only put two electrons in an orbital as long as they're spinning in opposite directions. And the truth is that if you look at the standards say for all of these things that you have to be able to utilize these electron configurations, be able to use them, interpret them, pull information out of them, etc., not necessarily write them. And I'm going to take that kind of approach as I explain these orbital notations to you. First of all, these are the electron configurations for aluminum and nickel carried over from the previous video, the video on standard notation. All the orbital notation is going to do is break all these electrons down into their specific compartments, their specific rooms. As we said earlier, an s orbital is just one orbital. There's only one room. P orbitals are actually a set of three separate compartments, each one holding two to give us that maximum of 6. D orbitals are actually 5 separate compartments. Again, each one holding a maximum of 2 electrons for our total of 10. Let's take a look at the electron configuration for aluminum. We're not going to have to do much with the 1s orbital. It is just one compartment, and in there's one electron that's spinning clockwise, one that is spinning counterclockwise. And what this is showing us is that we have one room, 2 electrons spinning in opposite directions. The 2s orbital will look just the same. Again, one compartment, 2 electrons spinning in opposite directions. So when we get to the p orbitals and the d orbitals that we have to actually do a little bit more work. We have to recognize that 2p is actually a set of 3 orbitals. And to get those 6 electrons into it, we put 2 in each orbital, spinning in opposite directions. So 3 compartments, each with 2 electrons, giving us that total of 6. Again, the S's are easy. It's only the P's that have to be broken down. When we get to 3p, we do have to draw all 3 of our spaces, but there is only 1 electron in it, so only 1 arrow to draw. Here's the thing. If there had been more than 1 electron to put in that p orbital there, what we have to do, what the Pauli exclusion principle tells us we have to do, is we have to put 1 in each of those empty boxes first, and then we have to come back and double them up. So let's say instead of doing aluminum, we had done sulfur. The only difference between aluminum and sulfur's electron configuration is that p orbital on the end. It has 3 more electrons in it for a total of 4. So if we wanted to show these 4 electrons in this p orbital, what we would have to do is put a single electron on each blank first, because that's the best scenario. They don't have any partners, they don't have any repulsion whatsoever. And then start doubling them up. And again, to get them to double up, we have to have the opposite spin. So it would end up looking something like that. Interpretation-wise, it's the same as interpreting a regular one. We have 3 energy levels. The first level has 1 orbital, the s orbital, and it's got 2 electrons in it. The second level has 2 orbitals, the s and the p. The s orbitals have 2 electrons in it, the p orbitals are full, with a total of 6. Level number 3 has 2 orbitals, an s and a p. The s orbital is full. It's got 2 electrons in it. The p orbital is not full. It only has 4, and it has room for 2 more. And that's working with sulfur. Let's take a look at nickel. Again, s orbitals are easy. There's only one room. 2 electrons spinning in opposite directions. 2s. One room, 2 electrons spinning in opposite directions. 2p. The p orbital is 3 rooms. This one's full with 6. So 2 electrons in each room spinning in opposite directions. 3p. I've got 3p, 3s. One room, 2 electrons spinning in opposite directions. Thinking ahead of myself. 3p is 3 rooms. We have 6 in there, so it's full. 2 in each room, spinning in opposite directions. Then we move to 4s. Now I could keep working off in this direction, or I can just move on to a new line, which is what I'm going to do here. 4s is 1 room. It's got 2 electrons in it, so it's full. Make sure they're spinning in opposite directions. Now we get to 3d. Again, the d orbital is 5 rooms. And the same rule applies with the d's that we have with the p's. You have to put 1 in each room first before you can start doubling them up. So, we've got 8 to put in there. 1, 2, 3, 4, 5. Now we can double up. 6, 7, 8. Oops, missed the first one. I backed that up. Hold on. 6, 7, 8. I missed this first line over there, didn't see it. And again, that is going to leave 2 of our rooms unfilled. We cannot put this arrow over here because that would require more energy. We have to keep them in separate rooms that way. And again, as we interpret it, when we look at this set of d orbitals, we can see that it's not full. We have room for 2 more. 3 of our d compartments are full, but 2 of them are not. We have room for 2 more before that d orbital would be filled up.